Okay, great. We're recording. It's week 9. We're talking about maps. Let's get started. Okay, so today we're going to cover two concepts in mapping. One is just going to be basic mapping, which is the one that I'm really good at using. And the other one's advanced mapping, which I always ask somebody about. In basic mapping, we can just use ggplot2 more or less. And this is just mapping with raw ggplot2 using coordinates like latitude and longitude. There's a wrapper for doing so called ggmap. That's for matching up maps with ggplot2. And we're going to talk about labeling points and using ggrepel to avoid overlaps. Then we're going to talk about advanced mapping. This is going to include things like simple features and the geometry that comes with those, as well as tidy census and Tigris for obtaining Census Bureau data and shapefiles. I'm realizing now I probably should have included something about leaflet. I'll cover that when we get there. A quick plug about mapping in R. There's this really wonderful textbook that's been out for a long time, probably since, I don't know, probably since I graduated high school. If you're interested in mapping, GIS and geospatial analysis in R, acquire this book. It's available for free, as all good R textbooks are. This one's at rspatial.org. The person, Edzer Pabesma, is working on another one. I don't know when that's going to come out, but be on the lookout.
The free ones obviously are only online. Like if you want the actual book.
Right, like if you want the hard copy, it's still, you'd have to pay for them to print it. Of course. You may also consider taking John Wakefield's, John O's class, CSSS 554, Statistical Methods for Spatial Data. However, it is quite challenging and focuses more heavily on statistics than it does mapping. But I only ever hear great things about it. I couldn't make it work in my schedule. I haven't taken it, but I've always been meaning to, and I've just kind of kept kicking the can down the road. CSDE, our Center for Statistics, Demography, and Ecology, offers great workshops using QGIS and ArcGIS. I also would recommend QGIS since it's free and it has a lot of great features and an incredibly large user community because it's free. Yeah, that's that. Let's talk about some basic maps. So I'm going to use that one day of SPD incidence data that we had from week 5 in those slides. We looked at types of incidents from the SPD responded to in a single day. Here, I'm just loading in the data from my GitHub. Checking a glimpse of this data. And we'll see the key thing for us today are that the longitude and latitude are logged and go to 4 or 5 decimal places, which tells us it's very specific. Since we have the latitude and longitude, we can just plug them in as X and Y coordinates on a ggplot. So we can provide to the aesthetics, the X and Y values, the longitude on the X and latitude on the Y. This is ideal when you don't need to place points over some map for reference. For instance, all of us have seen a map of Seattle, and we can kind of tell that this is a map of Seattle just looking at the way the dots are clustered and knowing what the data is like. So here I made a ggplot, and I've just given it a scatter plot. I've also used coordinate fixed, which just makes the same increments distance for all the things on the X and Y, which is okay when you are mapping things sometimes, if it's pretty close up. If you get into larger spaces, then the curvature of the surface makes it, you have to think a little bit harder about doing this. But sometimes we'll want to put these points over a map. So we have the ggmap package for doing so. ggmap is a package that works with ggplot2 to plot spatial data directly onto map images that are downloaded from Google Maps, OpenStreetMap, or Stamen Maps. One thing to note is that Google Maps requires an API key. It's really easy to get. You can't query it that much. I think you can do something like 10,000 a day, 50,000 a day, something like that. If you're geolocating things and you only have a free account. There are free options that can do this, but it might be a slightly slower. Yeah. So what this package does, ggmap, it queries servers for a map using the getMap function at the location and scale that you want. Then it plots the raster image as a ggplot object. It lets you add more ggplot layers like points and density plots and text on top of that layer that you've downloaded. It also has additional functions for interacting with Google Maps, things like getting the distances between bikes if you're doing the optional assignment. So installation, we can install ggmap just like other packages. But because the map APIs it uses changes frequently, sometimes you may need to get a newer development version of ggmap from the author's GitHub directly. This can be done using the remotes package. So if you run this little piece of code will basically say if you don't already have this installed, install it and then run it to give you the library to use remotes. And then this one will take directly from the person who's handling ggmap, their GitHub, and we'll install it just like any other package that you can call. This is a really solid way if you're really onto one type of package to just make sure you have the newest version all the time. I'd say that more often than not, things on the CRAN are what you want. But sometimes when there's like a new stats thing that you like to do, you might want to take it from the GitHub. Also note, this may require compilation on your computer. Compilation, an explanation of how to do it in both Windows and on Mac is on the course website. So let's look at a quick map using the qmplot function that is available through ggmap. qmplot will automatically set the map region based on the longitudes and latitudes that you've given your data. So here we have the SPD raw data. Our X is our longitude, our Y is our latitude. And we've given it this purplish color and made them slightly transparent. And here, all I provided was the numeric latitude and longitude, and it placed the data points correctly on a raster map of Seattle. Pretty neat. Also, I use the as is function, this capital I. It's used here to specify the set rather than the mapped values. So that way we didn't get a color per dot, for instance. Note that it's guessing a little bit on how to construct the picture. And so sometimes it'll be slightly amiss, but I think it did a great job. The getMap function is sort of underlying the qmplot and qmap functions. This retrieves the base map layer. And some of the options that are available for it are things like the location, where you can use a search query or a numeric vector of longitude and latitude in order to get that base map layer. There's a zoom, which is given in numbers, where like a 3 is continent and a 21 is building. The sources that are available are Google, OSM, and Stamen. OSM is not currently available in the CRAN version of ggmap, but it is in the GitHub version. And I'm not exactly sure what's going on with that, but it is available sometimes. You can give it different types of maps. So like Google, you can ask it to get a satellite image or a roadmap image. Or Stamen, you can get things like, I want this with watercolor or with different kinds of backgrounds. Actually, prepared a little example. So we could say, our place of interest is the University of Washington, and we'll give to QMap that location, and we'll zoom into about 15. Again, I try to troubleshoot the distance that you need when you make these kind of plots. And then I like the watercolor one. I think it looks nice. And we'll see that it's asking Stamen for these like pictures. And there's University of Washington. Great. And I could, if I had some data, put points on top of this or what have you. I'll show how to do that in a second, but I think it's neat. So we can add things like density layers. So we call QM plot with no geom. So it defaults to just making points. Note here, I didn't say anything about what kind of plot I wanted, and it just gave me a scatter plot of points. Here I'm saying geom is equal to blank, saying don't just give me a default scatter plot. Use the same X and Y values. I want the map type toner light, and I want you to make it a little bit darker so that we can see these density polygons. Then I've given to the ggplot layer the stat density 2 dimensions. And in the aesthetic for the fill, note that the stat level indicates we want the fill to be based on the level of values calculated by the layer. So this is actually doing a calculation right quick to create the fill that we see here. Our geom is going to be polygon rather than a square or something, a different shape. And we're going to make it slightly transparent so we can see things on top of each other. And then we've given to the fill gradient, white for low amount of crime, yellow for middle, and red for high. And we can see that the amount of incidents that happened were mostly downtown. Cool. Do you have any questions so far?
On the University of Washington map, was there a label? Is that just a Google Maps like one?
Yes. This is, yeah, it just decided, you know what, Seattle Yacht Club, sure. Parrington Lawn, why not? We can also label points on our maps. Let's label the assaults and robberies specifically in the downtown area. First, we'll filter to downtown based on values that were eyeballed from our earlier map. So I just did this relative to the points that were available to me in the data. Then make a data frame of just assaults and robberies. So I'm going to assign to assaults our downtown data, and then filter for just assault and robbery in our event group. And then create a new column that's just the description of things that were in this category. Now let's plot the events and label them with geom label. This is just geom text without a background or border. So here we see that we can like label all of our points and see very specifically where each of these incidents occurred. I've included a different color here, an alpha as well, using that same as is function, this capital I.
This is strong on robbery versus robbery, like violence assault.
I'm not sure. One thing about this plot, though, is that the labels are on top of each other, and this might not be necessarily what you want. So one option that we have available to us is the GG repel package. You can try geom label repel, geom text repel, and so on. And here I've given the geom label repel for a layer on our GG plot. And what it does is it just moves the labels so that they're not on top of each other, and then gives us a line to what dot they're talking about. This is really useful on maps, and it's maybe only kind of useful on other kinds of plots. Okay. That was it for basic mapping. That's basically the only kind of mapping that I do for my personal research. But advanced mapping is really cool, and I've only really had to do it for a couple of RA projects. So I'm going to share with you what I know about that. Some terminology that will be useful for to us for the rest of the course are simple features, coordinate reference systems, and shapefiles. So there's a package called SF, short for simple features. And until recently, the main way to work with geospatial data in R was through a package called SP. SP works well, but does not store data the same way that most GIS packages do, and can be bulky and complicated and hard to work with other colleagues who are used to the regular way that GIS works. The more recent SF package implements the GIS standard of simple features in R. SF is also integrated into the tidyverse. Geom SF, for instance, exists in ggplot2. One thing I will say is that you don't need tidyverse things in order for SF to be a really wonderful package. And that has tripped me up before in confusion as I've read somebody's data or code that was not using tidyverse things, but made really elegant plots out of SF. The package is somewhat new and is updated very frequently, but it's expected to replace SP eventually if people would just give it up. The principal authors and contributors to SF are in fact the same people who make SP, but with a few extra developers for tidyverse. Because SF is the so-called new standard, we're going to focus on that today. Simple features. A simple feature is a single observation with some defined geospatial locations. Features are stored in special data frames called class SF with two properties. So you'll note that there are these data frames when you're using the SF package that you want as an SF and not necessarily as a data frame. One of the properties of these is the geometry. These properties describe a location that's usually on Earth. It's usually 2 dimensions, but it can support 4. I was racking my brain to think of a thing that I would need to map in 4 dimensions, and I cannot. I don't know what that means, but I've read the help files. I know that it can do it. Each of these geometries are stored in a single reserved list column. I didn't talk a lot about list columns this far in this class, but more or less, each of the cells of your data frame are themselves a list and have lots of elements inside of them. We tend not to look at these. When I'm working with spatial data, the geometry is not something that I'm going to manipulate. And the column that has all of these multitudinous cells of information that are describing the contours of very specific land masses are not things that I'm going to look at. The geometry will also contain a defined coordinate reference system that I'll explain a little bit more in a second. Simple features data frames also include attributes. These are characteristics of the location. Things like the population. These are often non-spatial measures that describe a feature. These are standard data frame columns that we're used to working with, but they're called attributes in a simple features object. One thing also to note, list columns require special functions to manipulate them. This includes removing them from your simple features. Coordinate reference systems. CRS specify what location on Earth geometry coordinates are relative to. Oof, my 7th grade grammar teacher is not excited about that sentence. That's okay. But this is, if we're thinking about our world as a place full of coordinates, the CRS defines where 0, 0 is. Okay? And everything else is a point that is relative to that origin. And the CRS defines where that origin is. The most commonly used one is WGS84. This is the standard for Google Earth, the Department of Defense, and the GPS on your phone. There are 2 common ways to define a CRS in the SF package. There are the EPSG codes. These are numeric codes which refer to a predefined CRS. An example would be our default WGS84 is described as 4326. And this EPSG code makes it so that you can translate to other CRSs what one you're starting with. So if you want to join 2 simple features, and one's in WGS84 and the other one's in NAD20, you're going to use EPSG codes in order to translate one to the other and have their different origins make sense to each other. Another way you could do this, what is not available in all of the geometries you might receive in a dataset, are proj4 strings. These are text strings of parameters that define a CRS. So an example would be NAD83, Washington North, and you would use that kind of information to translate to a second data set. This will often come to us with a little bit of information when you read it in. Things like latitude +1 is going to be described as 48.73. Latitude 2 is going to be 47.5. This is going to give us the type of ellipsoid that our map is going to be based on. And a relative distance from WGS84. Note that this one's already coming into us as WGS84, so all of these are 0. And the units in meters, that kind of thing. Do you have any questions there? Cool. Shape files. Geospatial data is typically stored in shape files, which store geometric data as vectors with associated attributes or variables. Shapefiles actually consist of multiple individual files. There are usually at least 3, but there are sometimes 10 or more. The .shp gives us the geometries that we're used to thinking about for. So this might be like, if you wanted to have a vector of points that described all of the Puget Sound coast, this would be housed in our .shp. Our .shx is our shape positional index, and this helps us put those lists of vectors that create the Puget Sound next to other geometries. And the .dbf, the attributes describing features. Often there will be a .prj file defining the coordinate system for us. This is what this proj4 strings is referring to. Oh, goodness, this footnote is the wrong number. That's on. So let's get into using SF. Here are some select SF functions. SF is a huge and very feature-rich package. Here's a sample of useful functions. STRead and STWrite will read and write shapefiles. geom_sf allows for a ggplot layer using SF objects. STASSF converts a data frame into an SF object. So sometimes you'll get a data frame that has the proper columns, but is not prepared to be used as a special feature. And so this is how you will convert that data frame to an SF. stjoin is a big one. It joins data based on spatial relationships. And this makes it like a key to joining lots of data sets, because they can read where they are in comparison to each other on coordinates, and you can just join lots of data together. You can think about very different data sets, like the bike data that we have and the census and the police data, and how those are all related. You could join those very quickly using stjoin, even though it would take very difficult and a lot of thinking for joining them based on like the time that they happened and the place that they were described to be. sttransform converts between CRSs in case one comes to you not as a WGS84 for some reason. stdrop geometry removes geometry from an SF data frame. Recall I said that you would need special functions to remove things like the geometry from a data frame. This is that. strelate computes relationships between geometries, like neighbor matrices and things that are adjacent, things that are far away, that kind of thing. stinterpolate aerial weight, that's what that AW is for. Aerial weighted interpolations of polygons. I recommend the dedicated aerial package for this. I have tried to mess with this before and it was a struggle for me. Let's see how you would load the data in. So we'll work with the voting table. We'll work with the voting data from homework 5. You can obtain a shape file from the King County voting precincts from the County GIS data portal, which is really wonderful, by the way. Not every county has it like that. We can load the file using stread. Note, I've loaded in the .shp shape file. I've selected the precinct by changing the name column to precinct and the geometry. So it's reading in this layer from my files back home. The simple feature collection has 25 or 2,500 or so features, which you might recall from that homework. We had like 2,500-ish precincts in our data. The dimensions are on X and Y. We'll see that the NAD type is 83. So it's maybe not the usual one that we're used to seeing, but it's one that we can translate easily. If you're following along, this is how you would get that shapefile. I don't know with the people in the room right now if that will allow to download, since this lab is weird. So I'm going to do a little bit of pre-processing so that we can make these maps. This is more or less just homework 5, but in like one chunk of code. I've read in the King County data, filter to the president race, string detect the precinct for the Seattle, selected just the precinct to counter type and sum of count, grouped by the precinct, taken only the counter types for Donald Trump, Hillary Clinton, the registered voters, and the times counted, and then recoded the counter type variable to be just Trump, just Clinton, registered voters as one word, total votes as one word. And then I spread here. Note that this is actually the same as pivot longer, but I used the old kind of doing that so that it would all fit on one slide. And then I mutated to make the percent votes for Dems and the percent votes for Republicans based on our Clinton and Trump recode that we had in the countertype column, and calculate a turnout just there. Filtered out is.na percent Dem, which are, I think, 2 precincts that had some, I don't know, I hazard to say irregularities in their voting, but that's kind of what it was. And then I left join the precinct shape. And since when you join together a set of mapping data and a regular data frame, so like a special features in a data frame, it will coerce to being just a data frame. I then have to convert it into an SF here at the bottom, even though it has the columns that would make it an SF. So if we look at a glimpse, we'll see that we have 960 rows. They're grouped by precinct. We have precincts like Seattle here, some percentage of votes for Dems, some percentage of votes for Republicans, the voter turnout in that precinct, and then our geometry column says a multi-polygon US survey foot, and has a bunch more information just here for our first cell. And in fact, this cell for like the first row will have lots and lots of information in it and subcells for it. And like I said, I'm just never going to look at that. That's none of my business. The geometry that exists in that column is things that I'm not going to manipulate, but that I can use for calculating distances and things elsewhere. So now we can look at a voting map. We can plot SF geometry using GMSF. So here we have a GG plot. We have our precinct votes SF data. Our fill is going to be percentage of votes for Dems. Here we have our GeomSF telling it that we want to plot our special features with this fill. Theme void, so there's no information around here. There's no outline. And I think it looks pretty good. Do we have any questions there? Cool. Let's talk about census data. I use census data a lot. A lot of my RA gigs have always been like, we need you to take the American Community Survey and tell us this about X or whatever. Let's talk about the way I think is probably best practice for getting census data in R. There's the tidy census package. It can be used to search American Community Survey and decennial. That's not how you spell decennial. Census for variables. Then download them and automatically format them as tidy data frames. These data frames include geographical boundaries such as tracks right there with them, right when you download it. It's great.
What's the decennial fee?
Every 10 years.
Really?
Yes.
I didn't know that worked.
I've misspelled it there, so I'm also embarrassed.
Oh, I don't know.
It's just the I. The first I is replaced with an E.
Oh.
Like DECA,
Okay.
descending. But there are other surveys available through the tidy census package. That's not just the ACS and decennial census. But the package utilizes the census API. So you'll need to obtain a census API key. And I'm telling you that this is a real website. I know it looks like a phishing scam, but this is really how it works. I'll show it to you. It's comedy. This is it. If you want census data, you can put in your organization name. I'm not sure it even verifies your email address, and then agree to a terms of service that you don't need to read, and submit key requests, and they'll send you one. Um, this is the real website. Yeah. um, an API, I don't know if we talked about APIs thus far. I don't think we have. An API is an application program interface. It's a type of computer interface that exists as the native method of communication between computers, often via HTTP, usable via the HTTR package in R. R packages that interface with websites and databases typically use APIs. APIs make accessing data easy while allowing websites to control access to that data. So sometimes this is like a bother. Sometimes you're working on a project and you want to get some base salary information and you're trying to use an API to get information from like Indeed or Monster or something. But since they get to levy what data you get not good data. I'm not salty about it. It's fine. But some APIs are really great. The Census API being one of them. A lot of like government websites for lots of countries, APIs are really great for getting good granular data. Some key tidy census functions. First, there's Census API key. This installs a Census API key. Note that you'll need to run this prior to using any tidy census functions in order for them to verify who is asking for the data and how much they're handing you. Load variables, loads searchable variable lists. You can give it things like the year, so a set census year or an end year of the 5-year ACS, or the data set. This sets the data set. You can see the load variables help for more information about what that means. But one thing that's really weird is that the ACS last year is only available as like experimental data because they didn't have like a high enough response rate due to COVID. So that's tough. The ACS is a big deal. You can also use get decennial spelled correctly here, that loads census variables and geographical boundaries. You can pass to it variables, so you can give it a vector of variable IDs, as well as the geography that you want the information at. So things like state, tract, block level, as well as the year. I don't remember how far back tidy census goes. I'm not sure that even IPMs have like the 1930 census. I assume that they do, but I'm not sure tidy census does. I haven't tried. You also will probably want to use geometries equal to 2 or true in order to get your special features. Get ACS does the same thing as get decennial, but for ACS data. So when you're searching for variables, we can load the tidy census library. And I put in my API key here when I was doing this, but I'm not going to hand you my API key, even though it's really easy to get. And I've loaded the variables for 2015 using the ACS 5-year. And if we look here, we have things like, this is the name of the variable in the data set, which is not very easy or pleasant to look at, but it's way more easy and pleasant to look at than if you would use the fact finder on the census website. That's really difficult to navigate and really difficult to get the data that you want. And it takes forever to download, and then you download it, it's the wrong one. And it used to be different when I learned R. But that variable name will tell you what information it contains, things like the estimate of the total amount of males who are 20 years old. You can also search by concepts, so things like sex by age. Things like the way that the labels are written in the tidy census package really, I think, drive home how useful regular expressions are and how quickly you could look for things this way rather than searching around the way that we used to have to back in the day. So let's get some data from King County. We'll get ACS. Our geography is going to be to the tract level. Our state is Washington. The county is King County. We want the geometry so that we can make some maps. And our variables are going to be these two that I was able to look up using the load variables function. Note that the output is too wide. With get ACS, the wide version of data is actually the tiny version of data. And part of that is because of the way that data are nested inside of each other when it comes to ACS and decennial census data. So let's see what they look like. We have 398 rows, things like the GeoID, which is like, I forget exactly where each of these ends. 53 might be the state, and then this is like the county, and this is the city and the tract. I don't remember off the top of my head, but that's how GIDs work. We have a name of the census tract, some data here for each of these variables that I've asked for. Note that I asked for two variables and they both ended with E. These are estimates, they're point estimates. And then this M here is actually the margin. And that's describing the margin of error around our point estimate here. And that's because the ACS isn't a census. It doesn't have everybody included. And so they're estimating based on the information from the ACS what these point estimates are. And they want to hand you an easy way to access how robust those estimates are. So I'm going to process the data. We can drop the margins of error for this case and rename the estimates and then mutate into a proportion of any black. So here we'll get rid of anything that ends with an M. So these are our margins. We'll rename this to total population. And this is going to be anybody who self-reports as being any amount black. And then mutate any black as a percent of anybody who self-identifies as black divided by the total population so that we can get a percentage. And then we'll map it. We'll take our King County data and then create a ggplot and fill with our any black variable, add our geom_sf, and note that it already looks for our geometry column and uses it. I didn't have to tell it that like you need to use this geometry column. It recognizes that this is a special feature and found it for us. Then I've added some coordinates using the CRS that has been given to me. This datum equals NA here means that it's not going to put latitude and longitude lines on the map. And then I pick a couple colors for low and high levels of any percent black in a tract. And that's the state of Washington, more or less, and the proportion any black in each tract. Although I think this graph looks a little bit weird. Can anybody put their finger on why it looks? The island's too low, that's one. There's something else in this to do with the water. It just includes water in it, like over here.
Water.
Yeah. Part of the reason that is because when the census draws tracts, they include water. And the logic of it is like, sure, I guess. I mean, that is still part of like the landmass. But for mapping purposes, it is strange to see just like this purple area filled in, even though that's a lake.
There are houseboats.
There are houseboats.
But I don't think that's representative.
No. I don't think houseboats would be out in the middle like that. To not include the peninsula? Oh, like over here. Yeah. Yeah, that's partly due to the ACS being only a sample. So like if they don't, for instance, I had to do this project where I was getting a sample of like domestic care workers in all over the state, and there was just no estimates for like Spokane, and I was like, but that's like a big area. Like, like I would really like to have that, but ACS sometimes doesn't have that kind of thing because it's a sample of like 30,000 people out of everybody. Yeah. But here's this really, really nifty function that Chuck, who used to teach this class, wrote in order to get rid of areas that are water. And I highly recommend stealing this. It's really useful. So I'll describe what it does. Okay, so we can replace the water with empty space. We create a function called st_erase. The function takes an x and a y argument, and it combines the y argument with our x argument. It then looks at the overlap of each of the geometries, and ones that are like slightly amiss, it will fix them. This right here is something that only wizards understand how it works necessarily. And then it'll look at the differences between the things that have been fixed and not. And in order to make it work, you have to specify where the water is. So he assigns to the KC water from the Tigris package. This mapping package just tells you where all the water is. So you can just ask it to say, where's the water in Washington in King County as a special feature, and it will just hand you back that information. And then you can create a new data set that is the King County data set, and then erase the water. And it works. It's really great. And now we can use that exact same data, that exact same graph, using Chuck's code to get rid of the water. And yeah, that looks a lot more like what I thought it would. Yeah, still no point peninsula. Excuse me. We can do this again, but for the entire state of Illinois. And I'm going to show you how we can sort of stack more of these on top of each other. So here I'm going to get the ACS data at the tract level for Illinois with the geometry, same variables. Again, we want it as the wide version of the data, even though that's not traditionally what me and you have been talking about as wide data so far in this class, and create the same variables. We're going to use the same ggplot in order to create our plot. And it seems pretty clear here that probably for reasons of like great migration, that there's a lot of Black folks who are clustered in cities in Illinois. But what if we could verify that sense that we're getting? For instance, if we don't really know where any of the cities are in Illinois. One thing we could use is multiple geom SF layers. This is useful for adding points, let's say cities and states, or crimes on police beats, adding lines, so street grids on top of tracks, for instance, or adding outlines or highlights, things like elevation contours from topographical maps, or showing urban boundaries. So we can add urban outlines. We can use the Tigris package to download urban boundaries and then add them to our prior map. So we're going to take we're going to assign to urbans from the Tigers package, urban areas. CV is equal to true. This is sort of simplifying the boundaries that we're asking for. And this is typically okay when we're as zoomed out as the state. If we want more granular maps, we probably don't want CV to equal to true, but for here, that's fine. And when we look at it, we'll see a lot of information that is mostly just for us to get these polygons. And then we will get filtered down to just Illinois. So we'll have our same structure for our ggplot. We'll add a layer. Here we'll add it and include our data for urban Illinois. The color of the outline is going to be black with no fill, very thin lines, and don't take on the same aesthetics from up here. And now we can check against what we were thinking. The histories of Great Migration, having a lot of Black folks in Illinois in cities, seems to be related here and here and here. Pretty cool how you can just keep stacking them on top of each other like that. Yeah, I don't, like I said, I don't get a lot of mapping done in my own research, but I feel like with these tools, like, it's not as scary. It used to be a lot scarier when I first learned R. There is an optional homework 7. You can use the template that is on the course webpage to practice making maps using the restaurant inspection data. If you wish to submit this for bonus points, you can turn it in by next Tuesday. I will not be assigning peer reviews for this, of course. I will grade them all. And that's it. Thank you all so much.